cover, we just have this unit we can cover into 3 lessons, means 2-3 sessions, okay, and after that we just have a 1 unit left. So with that, thinking that, okay, at least I'll not take much time with on this module, okay, so that we'll have a time to do the revision with the for the face test, okay. So and last unit is AC to AC converter, okay, that we can use. See that it will not take much time on that last unit, cycle converter, or we're just converting from AC to AC, okay, that fixed AC to a variable AC. So that will not take much time. So what we are seeing on this is the inverter, okay. Inverter, you know, that is a conversion from a DC to AC, and most of the time, okay, these inverters are used in either in used either in UPS, uninterrupted power supply, okay, UPS, or it can be used in different where there is um, DC supply, okay, you require AC for at the end. Can you please switch? I think some of you. Let's see. Okay. So all this, okay. Last time, okay, we were. You must have attended. Okay, some of you might have attended the seminar presentation of B4P. Okay, some of you do not know whether we have a UPS in our department or in the college also, because when we ask them, okay, do we have a UPS in department? No, some of them they don't know whether we have a UPS or not, and what is the UPS, what is the rating of the UPS, and how do you calculate the load, and what should be the rating of the, all these things are, nobody will teach you, okay, but these are the things, okay, which you need to know yourself. So what is uninterrupted power supply, UPS? So what's the full form of UPS, and what are there inside the UPS, okay, what is the function of the battery bank, okay. We have a dual hybrid system in administrative block, okay, where we have a solar as well as a battery bank is also there, okay, and we have a grid connected system. So both can be the functions of both can be used on this, and most of the time, okay, we do not connect our UPS to inductive load, let's say our AC or even a fan, ceiling, and we don't connect this to inductive load. And please try to find out this. We have already seen the effect of the inductive load, or what will be the effect on the waveform, okay, and what we have if we have a pure resistive load, what is the effect on the on the system. So please try to find out all these things, okay, so that you try to relate with the practical things. You learn so much of theory, okay, but we forgot to correlate with the practical applications. And these inverters or rectifiers are used, okay, if it is a 3-phase inverters or if it's 3-phase rectifier, okay, these are used in a HVDC system, high voltage DC transmission systems. So when we when it is a high voltage DC transmission system, okay, the input might be AC, that has to be converted into DC, and you transmit the power in the form of DC. Then at the receiving end, again you have to convert that DC into an AC. So you require an inverter, and both the rectifier and the inverters are required in both the end. So these are some of the things you need to, where we practically use this type of systems, okay, conversions are required. At the same time, only we don't use the inverter, just an inverter and rectifier. There are so many other auxiliary equipments, okay, we need to use. Especially there will be, when you talk about the AC, okay, then the harmonics will be there. So how do we remove these unwanted signals, harmonic signals from the systems? So there will be so many things we need to understand on this. And for the high power application, okay, the thyristors are used, okay, for the low and medium power application, gate control turn of device like power BJT or MOSFET. we try to use all this, okay, and we know that we can classify it into BSI, CSI, or based on the circuit configuration, full or half type, and all this. There are so many like classifications are there in the inverters. Then whether it's the half bridge BSI, half bridge PSI, or full bridge BSI, okay, we can even classify it as half bridge and full bridge. So we have been talking about the half bridge, full bridge from the beginning of the of our courses. Okay, we have been talking what is a half wave, full wave control, half wave control, and similar to this, even in the VSI, okay, voltage source inverters. So there are half bridge and full bridge. Even the CSI, we can have a half bridge and full bridge. And last, even we can classify this into line commutations or the force commutations. In the CSI, okay, we can have a DC, constant DC supply, okay, at the input of the CSI current source inverters. So commutations can be possible, okay, force commutation or the line commutations, okay. It will actually, we are just talking about the switch, okay, and switch will depend on the at what angle are you firing that switches, that thyristors, and the output frequency will also depend on this. Now, when we talk about the inverters, okay, the input is DC. So we don't talk about anything about the frequency. In case of a DC, the pure DC, okay, we don't have anything. We don't have anything as such as frequency in case of the DC. But what we require at the output is we require uh, frequency at a different frequency, output at a different frequency level, maybe a supply frequency 50 hertz, or maybe if you are trying to control at the output, okay, the output voltage can be controlled, or the frequency can be, voltage can be controlled, external control, okay, we can have auto transformer, okay, conversion from a DC to AC, we can have a auto transformer. In some cases, even we can have, if we are talking about the internal, we can have a pulse width modulation control. But this controlling, if we try to use a transformer, okay, at the controlling the output voltage, okay, the transformer will have the effect if there is changes in the frequency. If the frequency are increasing, if we are talking of the more than the 50 hertz, okay, then this transformer may not work properly. Maybe this transformer designed for the supply frequency. So if we are talking about a higher frequency level, higher than the 50 hertz, okay, then this controlling mechanism may not be feasible, but you need to look at some of the things which is having an internal control. So these things, following type: series inverter, parallel inverter, auxiliary commutative inverter, okay. So these are the different, they means people have different, people try to differentiate between a different type of inverters, okay, based on the requirement, okay, like MC Murray, maybe person which based on their name, okay, they have a modified form of inverters. This is similar to this, like complementary commutative inverters, okay, are MC Murray, Bedford inverters are there. So there are so many different types of inverters. We'll try to look few of this. We will not go in detail on all this different type of inverter. But if you understand what is inverter and how does it operate, then that is much more. That will be much more helpful for you. I know that if we start looking at all those different type of inverters, we cannot finish our syllabus. Also, even we can have a module on this particular as an inverter also. So there are so many things, okay, if you go in detail on this different type of inverters. So in a single phase voltage source inverter, which I have looked at in last classes, okay, that half bridge inverters, okay, where switch S1 and S2s are used. And in this case, if you do not, if the load is purely resistive, G1 and G2 do not have much function on this. But in half bridge, if the load is inductive load, then G1 and G2, which we have already seen that the D1 and D2 will have a function on this. So based on the triggering of the switch S1 and S2, whether it is a low power or medium or low power inverters, or for the higher power, for power applications where thyristors can be used. So based on the triggering of the SCR, means like firing at what angle are you going to fire this. So we have already seen this half wave, okay, half bridge with RL load. Also we have seen the half bridge. It will start from the maximum negative current to, it will go up to reach up to T by 2. It will reach up to the maximum I naught, okay, then but the voltage will remain constant on that particular point. So similarly at D1, when it is D1, the both current is negative but the voltage is positive, which we have seen. And the switch S1 will conduct both the current and voltage will be positive, which we have already seen. These are the different mode of operations. We have already seen this in last class. So now we'll go to single phase full bridge inverter with R load. Similar to this, single phase full bridge inverters with R load. The drawback of, there are certain drawbacks on this half bridge inverters, okay, half bridge inverters, but in full bridge inverter we can overcome this. Similar to this, we can have the switches can be turned on at the similar to this, okay, S1 and S2 can be turned on, means triggered at a particular point, and this is the waveform for as shown when the IG1 and IG2, that when the switches S1 and S2 are triggered with the help of the gate signals at IG1 and IG2, then the voltage will be V0, output voltage will be V0, and the current will be V by R. If the load is resistive load, then it will be V by R. So current I0 will be, at this point it's S1 and S2 is triggered. So this is the operation, okay, between 0 to T by 2. At this point, okay, 0 to T by 2. At this point, okay, at this point, S1 and S2 are triggered, and S1 S2 are forward biased, and it is gated. It just means that S1 and S2 are the switches which is in forward bias, and it will be gated, means it's to turn on the SR. It means that it has triggered, means it's triggered. S1 and S2 are triggered. The output voltage will be V0 will be equals to V. So V0 will be equals to output voltage will be equals to V at this point. So, and the current will be equals to I0. So if you see, to find out the current is V by R. So current will be I0. So this is the current path. V, S1, A, then B, then S2, then it goes to N, then V. If you see, this is the path. V, S1, A, load, B, S2, N, and V. So this goes in this way when S1 and S2 is triggered. So V, S1, A, load, B, S2, N, and back to V. So this is the current path in case when the S1 and S2 are triggered. At T by 2, at this T by 2, then S3 and S4 are triggered. But the voltage will be negative V. Voltage will be negative V, and at this point. So at T by 2, S1 and S2 will be turned off, and S3 and S4 are turned on. So it means that S3 and S4 are triggered by gate current with the help of the gate current IG1 and IG3 and IG4. But at this period of time, IG1 and IG2 will be, means S1 and S2 will be switch off, means it will be off, it will commutate it, and IG3 means that S3 and S4 will be triggered at this point. And if you see here, voltage will be negative V and the current will be minus I0. So if you see here, the voltage will be negative V and current will be minus I0 during the other half. So similar to this, load current can be equals to V by R. So if we have a load, RL load, inductive load, then it will start from the negative current, negative I0. Okay, negative I0 when the D1 is 0 to at this particular point. So this is similar to what we have seen in, it will start from negative maximum peak negative current, then it at when the D1 and D2s are triggered, these two, that D1 and D2 are triggered at this point, then the voltage will be positive at this point. Now the voltage will be positive at this, and at the same time S1 and S2 are triggered, then it will reach to maximum current I0. Okay, it will reach to this maximum current I0 at this point. Again, the current will discharge and goes back to this particular point. So at this D3 and D4, this is exactly same what we have seen in the half control inverter. In case of a half, means like in a half bridge inverters. So in a full bridge inverters, means the working principle are exactly same as that of half bridge inverters. Now series inverters, okay, the inverters can also be a series inverter, it can be a parallel inverter. Commutating elements are connected in series with the load. In this case, the commutating elements are connected in series with the load in this case. Now commutating elements, so what is commutation? Okay, it means making, let's say, stuff conducting. Commutating elements are can be L and C, are connected with series with the load R. Now, in this case, okay, circuit so formed should be underdamped in nature. Now, I just want to please try to find out, okay, why do you need to have a circuit underdamped in nature? So please try to find out that why not the circuit can be overdamped? Why underdamped? What is the reason behind this? That circuit should be underdamped in nature. Now, circuit diagrams and waveforms are shown below. Okay, this is the series inverter where VS is the source voltage, T1 is the main SCR, T2 is the supporting SCR, L and C are commutating element. Okay, these two are the commutating. These two are the commutating element. This is the main switch, main thyristor. This is the auxiliary thyristor, supporting thyristors. With this L and C are commutating. This is the load. Okay. Now this is a series inverter. So T1 is the current flowing through T1, and I naught is the current through the load. So I naught, okay, the current to whatever current is flowing through this is flowing through the load. Now what happens? This is the waveform, okay, for series inverter. Now what do you understand from this waveform? When you trigger a main thyristor, suppose this is the main thyristor T1. T1 is the main thyristor. When you trigger this thyristor IT with T1, what happens? What do you understand from this? It will, the current, output current I naught will reach to the maximum point and fall back to 0. Because the condition is in this one is that the circuit so formed should be underdamped in nature. So circuits, it will reach to the, because of underdamped in nature, because of the nature of the circuit is underdamped. So it will reach, the current will reach to the maximum and fall back to 0 at point A. Then this is a point where both the thyristor T1 and T2 is off, means between A and to B. So at this point, because when you trigger this thyristor IG1, gate thyristor, main thyristor IG1, the output current will reach to the maximum point and fall back to 0 at point A. So at this point, 0 to A, the current is reaching to maximum and falling back to 0 at A. And at this point, both the thyristor T1 and auxiliary thyristor, both the thyristors are off at this point. Let's see here. At t equals to 0, T1 is gated. It means that T1 is triggered. The thyristor, this T1 is gated, and it means that this thyristor has a forward bias and started conducting. And T2 is not gated. It means that thyristor T2 is off. So T2 is off. The gate current I naught will be equal to IT1. So I naught will be equals to IT1. So the gate current will be, when this thyristor is IT1 is conducting, this gate current will be equals to I naught will be equals to IT1, current flowing through this thyristor IT1. So as the nature of the circuit is underdamped, I naught reaches its peak value and then fall back to 0, say at 0. So it reaches to the peak value and fall back to this 0, because on underdamped nature of the circuit in series inverter, it reaches to the maximum value and fall back to 0. Please note down this. Please try to understand these things quite clearly, because I told you to please try to find out why the circuit should be underdamped in nature. So if you go through the textbook, you'll find out this, that why do we require to have the nature of the circuit should be underdamped. And it will fall back to 0, say at A, and up to this point the capacitor start charging. So this capacitor will, these two are the L and C are the commutating, these two are the L and C, okay, are the commutating element. These two things, L and C are the commutating element. At this, when the thyristor T1 is conducting, then the capacitor will start, it will be charging. So up to this point the capacitor starts charging. At t equals to A, at t equals to A, at this point, when t equals to at A, it reaches to the maximum, current reaches to maximum, fall back to 0 at point A. At t equals to A, T1 is off. So when t equals to A, it means that it fall back to 0. Okay, then it means that this thyristor T1 is off at this point. This thyristor T1 is off at this point, and at t equals to E, T1 is off due to reverse direction of I naught. So till TB, till TB between A and B, it is off. So till TB, T2 is also off. So both the thyristor T1 and T2 is off during between this A and B at this point. Hence, the current will, when both the thyristor T1 and T2 is off, then the current will be, output current will be equals to 0. That's why there is no current in this between A and B. Output current equals to 0. So, therefore, the period AB is called the turn-off period. So, this is the period which is known as a turn-off period, because both the thyristor T1 and T2 is off. Main thyristor and auxiliary thyristor, both the thyristors are off at this particular point. So off. So T off is always greater than the SCR turn off time. So it means that turn off time T off is always greater than the, you know that what circuit turn off time and device turn off time means, that what is the total, means like the device, the component turn off time should be less than the circuit turn off time. So that in this case the T off is always greater than the SCR turn off time. The SCR turn off time is TQ, minimum turn off time is T off should be always greater than this. So within the period of this period A and B, within this period, at this period, okay, within this period off period, so T1 and T2 are off, the load terminals are open circuited, both the thyristor T1, main thyristor and auxiliary thyristors are both off, are open circuit, and the capacitor charging voltage remain constant. So it means that capacitor charging voltage will remain because there's both the thyristor T1 and T2 are off. The voltage across the inductor is given by. Now, if you try to find out the voltage across the inductor, that commutating element as C and L, so voltage across the inductor will be equals to minus L di by dt. This is the common equations. So at t equals to B, so at t equals to B, at this point, at t equals to B, T2 is gated. Now it means that T2 is gated at this t equals to B, because if you see at this point now, thyristor T2 is gated. This is a pulse is given to our thyristor T2. So it means that triggering is gated at, means thyristor T2 is gated, auxiliary thyristor is gated. At this period, T1 is off. So T2 is gated and T2 is operating, is in operation, is in forward bias, and when you give a triggering to T2, then it is, so T2 is gated and T1 is off. Loop is formed through T2 R, C and L. T2 R, this T2 R, C and L. This is the gate formation of the gate. So it means that when T2 is on at this point, so I naught will be minus I naught. So the current will be negative maximum. It goes to when the T2 is on, so it will be minus I naught. So it will go to the maximum negative I naught, then again back to 0 at this point also. So now the capacitor will start discharging. At this point, the capacitor will start discharging at point T equals to C. At this point T equals to C, again it will go reach to maximum negative current, then fall back to 0 at C. Now at T equals to C, I naught is equals to 0. So at this point, I naught is equals to 0. Again at duration C and D, the current will be equals to 0, similar to that of A and B. So implies T2 is self-commutated, means it's a self-commutated thyristor, so it means T2 is off at this period. So during C and D, capacitor voltage remain constant. Again at T equals to T, T1 is now the same cycle will flow. So if you see here, now initially thyristor T1 is triggered, then it reaches to a maximum value of current and fall back to 0. When T1 is on, now at the point T equals to A, then thyristor T1 is commutated. Key. It means that thyristor T1 is off. At the same time, T2 is also off. The current I naught will be equals to 0 between point A and B. Now, when the thyristor T1 is off and auxiliary thyristor T2 is on, then from B, it will reach to the next maximum negative current, then fall back to C, means fall back to 0, I naught equals to 0. So at this point between C and D, both the thyristor T1 and T2 will be off. Again, now the same thing will continue, as it will just be a repetitions, whatever we have seen at the. So this is the means capacitor voltage will reach to, this is the source voltage, it will be charging at the maximum, and it will be again discharges at this particular point. So this is a charging capacitor voltage. Now source voltage will be positive, and it goes to, this is the time when there's it's a T off, means off period of the time. So it's a off period. So it's quite simple, means if you try to see this capacitors, means like series inverters is having a two thyristor T1 and T2. This is the most simple type of thyristors, means simple type of inverters, where you require only two thyristor T1, and one is main thyristor, other one is the auxiliary, and we require commutating elements like L and C are the commutating elements, like commutating element, this L and C, and you have a load. Okay, when T1 is on, then the I naught will be equals to IT1, and similar to it will be charging, and discharging will take place, current will reach to the maximum point and fall back to 0. Now let's see a little bit on this. Okay, voltage control, voltage and frequency control of single phase inverter. Now how do you control the voltage and the frequency? Voltage control in a harmonic reduction inverter. Now when you talk about this voltage, okay, how do you control the voltage as well as same time? I think the frequency is not given here. The frequency can be, we can control the frequency also. The frequency control can be possible with the help of the firing angle of the switches, firing angle of the SCR. So output voltage can be possible. Now output voltage will, what we require, especially in case of a pulse width modulations. We'll talk about later on single pulse width modulation or a multiple pulse width modulation. So what is happening is that you will have a modulation, means when you talk about this modulation, we talk about the carrier, and we talk about the input signal. So whatever is the input, okay, we try to see that T is equals to 1 by F, total time period, in one period, one cycle, then the frequency will be equals to T equals to 1 by F. So we can find out the frequency on that particular, when cycles is one full cycle. So at the same time, we can control the output voltage, we can reduce the harmonic, because harmonics are the unwanted signals, and we can remove this with, there are so many techniques like harmonic reduction transformers are also there. There are so many other techniques which can remove the harmonics. So the voltage control, the controlling the voltage. Now why do you need to control the voltage? There are three different types of voltage control: external control of DC voltage, external control of AC voltage, and the internal control. So these are the three different type of control: external control of DC voltage, external control of AC voltage, and other one is internal control. Now external control of a DC voltage, okay, how do we control the external control? How do we control the voltage? Now if the input is suppose, let's say in a HVDC system, or let's say in case of a UPS, uninterrupted power supply, now we can control the voltage with the help of the chopper. We have already learned what is chopper, right? So where the fixed DC is converted to a variable DC. Now if you try to control the DC input DC voltage in an inverter, we can control the voltage, output voltage. So we are having a regulator at the input side itself. So that is one way of controlling the voltage. So if you see the first method, the output voltage of the inverter, these are the following methods: controlling the input voltage to the inverter using the phase control rectifier. You can use the phase control rectifier because we are rectifying, we are converting. You can use the rectifier also if we are converting DC to AC. Okay, DC to AC, because these things are quite important if you try to analyze the HVDC system, high voltage DC system, because we are using all these different type of converter. Input is AC, then we are converting this AC into DC. Again, this DC is transmitted in a DC transmission line, and at the receiving end again we are converting this DC into AC. So we can control the voltage, okay, at the input itself using the control rectifier, phase control rectifier. We're converting the AC into DC. Rectifier means we are converting AC into DC. So the controlling mechanism can be possible here itself. The other way of controlling is that we can use a chopper. After converting AC into DC, we can use a chopper where a fixed DC can be converted into a variable DC. That's our other way. The effective value of the output voltage varies in direct proportion, and in the ideal case, VL equals to load voltage equals to V. So in this case, the peak value of the voltage is controlled. So it's a peak value of the voltage, which is also known as amplitude control. The output voltage can be varied by an auto transformer, which I've told you at the beginning of the class that output voltage is the external control of the AC voltage. But there are problems on this external control of AC voltage, because the inverter circuit will operate at a different frequency level, at variable frequency level. Now, if we use, you must have already learned what is auto transformer, okay, which operates on the supply frequency. Now, if the inverters circuits operates on at a variable frequency, then if the frequency range is wide, then the use of auto transformer is undesirable. We cannot use the auto transformer to control the external control of AC voltage. So these are some of the drawbacks. So there are some control mechanism within the inverter itself. So that is also most common method used are the pulse width modulation methods are used in this case. These are the most common method used for the control of the inverters. Means that controlling the output voltage of the inverters. Pulse width modulation of the voltage may be employed. This is the internal control. Whatever I'm talking about previously, the external control of the AC voltage and external control of the DC voltage, these are the external control. Okay, pulse width modulation is the internal control, and the voltage on the load side may be controlled by means of voltage control. That is what we means. The means of a voltage controller. That is what we are talking about. And the other one is the harmonic reductions. Harmonic reductions can be used by using the filters. You know that we can filter out the unwanted signal from a device. Okay, the series of inverters are connected in series so that there is a phase displacement between their outputs. So this can also be used. This is the other way of reducing the harmonics. So provide the voltage control also simultaneously. So it can also provide the voltage control, and it can also be reduced. The frequency means like unwanted signal can also be reduced. I think I'll stop here today's class. Okay, I'll not. We have another things. This, I think we'll just finish this. Harmonic reduction by pulse width modulations, harmonic reduction by transformer connections, or harmonic reduction by step wave inverter. So these are the different way of reducing the harmonic pulse width modulations. When we try to do the modulations, okay, modulation means you need to have a carrier signal and input signal. This carrier signal is modulated with the input signal, and when you convert back to the original signal, okay, then we can reduce the harmonic. We can filter out the unwanted signal with the help of the PWM. And harmonic reduction transformer connection is, I told you that there are special type of transformer which is known as harmonic reduction transformers are there. So we can reduce the harmonics with the help of the harmonic reduction transformer to connect to our transformers. And by the step wave inverters are there. These are the different methodology used to reduce the harmonics, because when you convert from DC to AC, there will be a unwanted signal mixed with the original signals. So these are the different methods for reducing the harmonics. So I'll stop here. Okay. So before this, okay, I just want to take this. Just take a screenshot. Okay, I'll stop here. Okay, next class we'll see CSI, okay, current source inverters, and different type of like voltage control and frequency control. Okay, we see this pulse width modulation, single pulse width modulations, and a multi pulse width modulations in next class. How do you control the frequency? Okay, output frequency with this method, single pulse width modulation, multi pulse width modulations. And please go through the textbooks and prepare well for the FS test. Okay. So I hope that all of you are aware that the timetable, I have already circulated timetable. So please study. Okay, whatever the module tutor asks you to, whatever method they follow, okay, please try to do the face test initially. This will directly go to your face test marks. It will be out of 10. Class test might be maybe 2 marks or 1 marks, okay, but this will really have an effect on at the end of the day. Means when even this will have overall performance in your degree marks will also be affected if you do not take care properly all these face tests. Even at end semester exam, okay, this if you do not have a good marks in face test, then you will have a tough time okay, securing high marks even to getting through that particular module. So please study well. I know there are so much of challenges. Okay, challenges are there. Everybody is facing the challenges, but with these challenges, I think we have to keep aside all these challenges. I know sometimes because of the network problem, most of the time, okay, you are I know you are facing the network problem, but there is no other way. So please try to study, keep all those negative things away, and please do study well and keep stay. Keep, okay, I'll stop here.
Thank you, sir.
Thank you, sir.